as you said, this is part of an enforceable undertaking where we're performing an activity and the activity went wrong, and almost went wrong in the worst possible way. So first off, there'll be a couple of videos, and then we'll talk about the incident, and then we'll also talk about some learnings on the incident. So as I mentioned, we're going to do a rope handling informative. We're going to do the incident animation and their presentation. We also agreed that we'll do mental health awareness training, an induction pilot, and we'll do, support the Mates in Mining cause. And then we also agreed that we'll do an opal mining shaft safety video. So that was the content of our enforceable undertaking. So first off, before we do the videos, so a bit about SIEMAG TECBERG. So we are an international company. We've got presence on pretty much all continents, and we've got close to 400 employees globally. Our head office in Australia is in Glendenning in Western Sydney. So the key strength of SIEMAG TECBERG is we're one of a few companies that can provide all types of winders. So we can also integrate all drives from any supplier into our systems, and we can use in-house or third-party solutions for a lot of automation and control. So prior to the incident actually carrying out, we went through, did our normal process. We did a construction risk assessment, reviewed existing procedures, and we reviewed engineering design reports for the system that we're dealing with to understand all the design capacities of the sheaves in conjunction with our new equipment. And we familiarised the team with the rope removal procedure. So we thought we were checking everything before the job. We carried out factory acceptance testing of all our equipment to make sure it performed adequately. We delivered the equipment to site, set up all our barricading zones to prevent personnel from entering. We set up communication equipment for all our people around. We interlocked the emergency stop circuit between the friction winch and the winder. And then we set up and commissioned the field emergency stops for the personnel carrying out the actual installation of the task. So with all that thought process, we still got it wrong, and this video is about to just give you a brief description of how it went wrong, and then I'll talk about it afterwards.
In January 2020, a specialist contractor was engaged to upgrade the drift winder at a New South Wales coal mine. The contractor was required to remove the drift winder rope and developed its own procedure for the project. The winder rope was to be fed from the mine's drift winder through the existing head sheave to a mobile friction winch and then onto a rope reeler. The contractor undertook the rope removal during a planned shutdown on the 6th of October 2020. The task was performed by a work crew of 5 contractor workers and a mine worker. At around 12 p.m, crew members erected barricading taping to demarcate and restrict access to the work area. The crew believed they had approval to enter the work area. At around 12:45 p.m, some of the crew participated in a task analysis, which reviewed each step of the rope removal procedure, identifying relevant hazards and agreed controls to ensure it could be done safely. The task analysis identified equipment failure caused by over-tensioning as a hazard. Maintaining visual slack in the rope, radio communication, maintaining line of sight, and taping off restricted areas to keep workers out of the line of fire were the agreed controls. At around 4 p.m, the crew began removing the rope from the drift winder. This required simultaneous operation of the involved plant and coordination using UHF radio, direct line of sight, and hand signals to ensure sufficient slack was maintained. Tension in the winder rope increased, introducing significant force on the head sheave assembly. At around 5:53 p.m, the head sheave assembly failed and the 3-ton head sheave dislodged and fell 14 meters to the ground below. At the time, a crew member was on the ground directly below the head sheave tower within a taped-off restricted area. The worker had to evade the falling head sheave, moving clear moments before it hit the ground. No one was injured. The incident was reported to the New South Wales Resources Regulator, who investigated its cause and circumstances. The investigation found the primary cause of the incident was over-tensioning of the rope between the driftwinder, friction winch and head sheave caused the structural failure of the head sheave bearing assembly and hold-down bolts, which in turn dislodged the head sheave, causing it to fall. The over-tensioning most likely occurred when the driftwinder stopped unwinding while the friction winch and rope reeler continued to wind in the rope. Prior to the incident, a third-party engineering report was obtained, assessing the structural integrity of the head sheave tower and assembly. The report assessed a proposed 12-ton rope load based on the methodology drawing provided by the contractor. It found the head sheave shaft and hold-down bolts were non-compliant with relevant Australian standards and recommended an 8-ton rope load limit and that the hold-down bolts be replaced. The incident investigation determined the following key contributing factors. The project's overarching risk assessment failed to appropriately identify and assess the relevant risks and controls associated with the rope removal. The third-party engineering report's recommendations had not been appropriately addressed by the contractor. The friction winch was capable of exerting line pull forces on the head sheave assembly in excess of 4 times the 8-ton limit recommended by the third-party engineering report. The rope removal methodology lacked engineering controls to prevent the rope becoming over-tensioned, had no method of obtaining information in real time of the actual line pull forces being exerted, and had no method of remote task observation, such as cameras, eliminating the need for workers to be positioned within hazardous areas. The rope removal procedure did not incorporate higher-order controls, such as hard barricading, to create a physical barrier to hazardous areas in the potential drop zone of falling objects. The rope removal safe work method statement, procedure, and task analysis did not clearly define the locations, classification, and entry requirements for the barrier-taped areas during each specific job step. As a result, the workers were operating within hazardous areas on the premise that these areas were control zones which they had been granted approval to enter. It is recommended that persons conducting business undertakings who are involved in driftwinder construction, operation, and maintenance works ensure driftwinder rope removal procedures eliminate, where reasonably practicable, or otherwise minimize the risks associated with rope over-tension by using fit-for-purpose plants suitably powered and configured for the task, higher-order engineering controls such as load cells and interlocks preventing the exceedance of plant-safe working load limits, higher-order controls such as hard barricading to create a physical barrier to hazardous areas in the potential drop zone of falling objects, and remote monitoring devices such as cameras to eliminate the need for workers to be in hazardous areas. Ensure documented procedures clearly articulate exclusion and restricted access areas with clear instruction and guidance provided on the locations, classification, entry and exit requirements. And ensure workers have appropriate training and instruction in procedures and risk assessments so that requirements are clearly understood and adhered to. It is recommended that workers comply with implemented hazard identification and risk management processes to ensure that when conditions or procedures change, adequate new risk control measures are put in place. Always maintain situational awareness and never enter areas in the potential line of fire of falling objects. For more information and to see the full report, visit our website.
And now I'll just play the second video and then we'll discuss it.
In October of 2020, SIEMAG TECBERG Australia began the on-site installation portion of a driftwinder upgrade project at a colliery in New South Wales. During the removal of the winder rope from the driftwinder, the head sheave was dislodged from its support frame due to excessive tension on the rope. and fell approximately 13 metres to the ground below. Following the incident, SIEMAG TECBERG, formerly known as Winder Controls, made a number of changes within the business. The primary change was a management restructure to ensure that roles and responsibilities of each manager were better aligned with the requirements of their departments. SIEMAG TECBERG also implemented a company-wide action tracking system, which enables employees to more accurately manage tasks and to ensure that actions that come out of meetings and risk assessments are followed through. This also allowed the management team to have easy access to an overview of tasks and their status at any given time. SIEMAG TECBERG went on to successfully complete the installation of the winder in January 2021 and developed a new rope installation procedure using lessons learned from the incident. Additional load cells were implemented to monitor the rope tension. These consisted of inline load cells to monitor T1 and T2 tension on either side of the friction winch, and a sheave load cell to monitor the load on the sheave. All load cells were interlocked to the operation of the equipment in order to prevent excessive tension in the rope. CCTV cameras were installed to monitor key items of equipment which were previously being monitored by spotters. These fed to a control centre within the winder room and eliminated the requirement for personnel to be positioned in high-risk areas. 2 barricaded areas were erected around the rope installation area. The first, larger area was erected to restrict access to the area to only those personnel who were required for the installation tasks. The second, smaller area was erected as a no-go zone for all personnel while the reeler, friction winch or winder were operating. No one was allowed into this area at any times during operation. Noise-cancelling radios were provided to all relevant rope installation personnel. Rope removal was carried out by a team of 6 individuals from SIEMAG TECBERG. The winder driver, friction winch operator and reeler operator monitored the equipment using the CCTV displays and compared the load readings from the load cells and equipment readouts during the rope installation. A spotter was positioned on the tower to look down onto the friction winch and reeler and also to look along the length of the rope going into the winder drum. A second spotter was positioned alongside the no-go zone, looking at the inline load cells and the rope going through the friction winch. A third spotter was positioned some distance from the installation area, monitoring the rope slack between the sheave and the winder. The rope installation began by using an air winch and fibre rope positioned behind the winder to pull the end of the winder rope from the hydraulic reeler through the friction winch and around the sheave back towards the winder drum. Once the rope had reached the winder drum, the friction winch, air winch and hydraulic reeler were isolated and the winder rope was secured at the winder house window to an approved anchor point with poly rope clamps. The rope was then fed through the horse hole and into the rope anchor clamps. The inline load cells were then installed on the T1 and T2 sides of the friction winch. The hydraulic reeler was set to maintain a nominal tension on the back of the friction winch at T2. The friction winch and winder were then used to slowly apply a load to the rope, while the rope tensions were compared between the load cells, friction winch and winder readouts to ensure that all items of equipment were reading as expected. When the rope end reached the head sheave, the friction winch, hydraulic serve as a checklist for the industry to reduce the likelihood of future incidents occurring. This tool is designed to support the responsible person's decision by allowing them the confidence to proceed with the task or project or stop the task or project, knowing that too many questions are unanswered.
Bit of our mindset before doing the task. When we were going to do the rope removal, there was no need for any high tensions between that friction winch and the drum. So it was all going to be storage tension between the friction winch and the actual rope reeler that was in the shed. I guess that led to a complacency from our part on actual controls required to stop it in the event of something going wrong. So when the winder stopped, there was not enough controls in place to actually stop the friction winch from continuing to run and increasing tension, putting it into the tower and leading the actual tower sheave to fall down. That friction winch that was actually used, so again, it spoke about using suitable equipment. So the friction winch is a friction winch that we use all around Australia. It's designed to do multiple ropes at once, and it is designed to go up to 60-tonne capacities. Now, our people did set it up in the workshop to go less than that, but it was actually set up for the rope installation task, not the rope removal task. So post the incident, so we installed the actual planned rope sheave that was going to be installed as part of the actual changeout. So this increased the tower capacity. We commissioned the load cell system that was going to be used in the final winding system. Installed the secondary inline that were used to stop the winder if we did see any high tensions. We changed the readout screens on the friction winch, so the friction winch actually had a percentage motor capacity, not direct line pull, so it required our people in the field to actually try to do conversions, so we did fix that up. As you saw, we increased the barricading zone. We questioned whether or not the people actually needed to be there in the area doing the rope tasks, so then we went down to the CCTV systems. So with the CCTV systems, you guys install them all over your sites. You know how quality they can be now with the image and actual refresh rate. So we just made a decision to eliminate as many people involved in the task as possible and put cameras around and make sure that the drivers of the winders can actually see that. On the video, it actually showed one person standing between the friction winch and that shed. As you can see, they were actually in close proximity still to the sheave. They actually were removed, so that video is a little bit incorrect there, but yeah, they were removed from the area. We also changed, we installed the set point monitoring to measure the motor current and limited the capacity of the winder to not exceed that of the actual tower and the sheave. We changed the friction winch control system for the winch to be controlled remotely by the winder control desk. This included controlled stop scenarios as well as emergency stops. So prior to that, if the winder did a controlled stop, the friction winch continued to run. So we fixed that up and got them talking to each other. The friction winch was also set up without brakes. So it would, in the event of a stop, it would actually just release tension and nothing would go wrong. So the slack would go into the rope and it would be left in a safe state. So now, back onto the actual rope handling informative. So we all know the hierarchy controls. We live it, we breathe it, we see it all the time. As engineers, we're typically engaged to find solutions when elimination or substitution is not possible. So whether through site engineers or partnerships with firms like SIEMAG, TECBERG. So engineering controls we design are to address the hazard at its source and to eliminate, minimise or control the risk to as low as reasonably practicable. So through the use of adequately designed and installed equipment, well maintained to prevent the erosion of the hazard controls, these are long-term effective solutions. So when planning the tasks, we need to consider the use of engineering controls reasonably available to complete the job safely and effectively. So when carrying out rope handling tasks, we use line pull as the essential step to actually decide what we're doing. So line pull can be monitored using inline load cells attached directly to the wire rope. Strain gauges bonded to the wire rope used to measure the change in the actual rope length. Tension meters, similar to inline load cells, clamped onto the wire rope to measure the rigidity of the rope, and load indicators attached to the rope end or the rigging. So using that information, you need to make sure that you actually do something with it. Don't just put on a readout. Make sure that you can actually put that in sync with your mine equipment, so you don't rely on the human factor to actually make a decision. Structural considerations. So this is going down the mechanical path, but structural considerations are head frames. So we are now changing the load that you see that head frame is designed to see. So you need to make sure that you do your engineering assessments to make sure the load capacity, the structural integrity, the stability, wind and seismic loads and accessibility are all factored in to make sure that you can actually do that task adequately with the equipment and the site set up. So the use of deflection sheaves in rope work is common because you are not using the normal rope path to do your rope change out. So you're not using your winder, you're not using your head sheave as they were designed. You're typically introducing other equipment, friction winches, reelers, that type of gear. So you need to make sure that the sheaves themselves are set up and used in the rope system adequately. You need to make sure that they're going to actually reduce the amount of stress and wear on the rope. So quite frequently we actually see deflection sheaves that are incorrectly fitted for the system, and you actually cause higher amounts of stress and wear on the rope. So make sure you do have gear that is adequately sized. So the use of deflection sheaves with steel wire rope involves the following risks. So overloading the sheave or the structure in which it's mounted to. Misalignment. So misalignment can cause excessive wear on sheaves on the rope and reduce the rope life. Rust and corrosion can cause the sheave to seize or fail, which may cause loss of the load and potential injury to personnel. And then the actual maintenance of these sheaves. So a lot of sites have sheaves, they have them sit in their yards, in their towers, but you typically don't use them often. So you need to make sure that you are properly maintaining them and inspecting them to make sure that they are fit for purpose still. So the other factor we need to consider when doing rope change out is fleet angles. So fleet angles can have a hugely detrimental effect to the winding system and what it was designed to do. So the fleet angle, most of you know, is just the maximum angle that it'll see for the rope when scrolling across that drum. So obviously the highest risk is when you're at the maximum fleet angle, and then also your drum design when you're at the minimum fleet angle for the actual adequate feeding of that rope. So fleet angle is an important factor to consider when installing steel wire rope onto a drum or removing rope from a drum for the following reasons. So as mentioned before, fleet angle can affect the amount of wear on the rope, and incorrect fleet angle can cause excessive wear or reduce rope life. So fleet angle affects the coiling of the rope onto the drum, and incorrect fleet angle can cause miscoiling and or damage. So it's important to follow manufacturers' recommendations for fleet angle. So we need to make sure that all our equipment is set up for it. Now the tension side of things with drum winders. So the TRG does mention that we use 50% tension in ropes, and that there is to make sure that the dead turns that are not used in service are pre-tensioned, so you don't get any pulling of your wire ropes into the bottom layers, and you don't get any wear and grinding going on of your ropes. Some secondary reasons are the preloading of the rope to get it to its operating diameter. So they are normally relaxed in the larger diameter, and then you also want to prevent slip between that drum. So obviously we need to consider mine layout considerations. I'll just skip through these because we are running a bit behind, but exclusion zones are key. Make sure your people aren't in those exclusion zones and that they are adequately set up to prevent the actual interaction with the hazard. So the use of the CCTV systems, yeah, they are great nowadays. The actual refresh rates that you see and the camera quality, some of the systems that we set up on winders can see kilometres into the bloody background. So they are great to use, and people need to start considering using them wherever you can. So rope handling documentation, it's just like any other task. So we need to do our risk assessments, safe work procedures, training work records, permits, inspection records, and our plans when things do go wrong. We need to consider our labour force, their qualifications, and actually how frequently they do rope tasks. Consider communication on how you're going to actually carry it out throughout the task. So is it face-to-face? Is it using two-way radios? Is it hand signals, written instructions, signage? So just need to make sure that your people know what the communication method is going to be, and they do consider it actually prior to doing the job. So this is the rope handling informative. So it is actually on the Resource Regulator website, and it is a document that's about 20 odd pages, and it's there for mechanical, for electrical and mining engineers to consider all the different controls and factors in doing a rope change out task. So go on there, have a look at it, and it's just a baseline. It's just a starting point to get people thinking on what they actually need to consider when doing the rope handling task. All right, I'll wrap it up there because we are short of time. So that's me from SIEMAG TECBERG. Thank you.